Apologies for that. The app that I'm testing out to do these recordings cut me off at the 15-minute mark, apparently. So we left off just simplifying this math right here. 25 minus 16 is 9. 9 divided by 3 is 3, which means our common difference is 3. We still need to get the first 3 terms, so it's going to be easiest to find the general term and get the first 3 from there. We don't know a. We know 2 different terms that we could use for term n, and we know our common difference now, so we can find a. So let's start with this one just because it's going to have smaller numbers. Term n will be 16, so we're going to sub all of this information into the equation. So term n is equal to 16. We don't know a. N is the term number, which is 5, and 5 minus 1, and then we know our common difference from over at the side is 3. So we simplify this. 16 is equal to a. 5 minus 1 is 4. 4 times 3 is 12. So a plus 12. 16 minus 12 is 4. So our a value is 4. We put that back into our general term. So we have a is 4 plus n minus 1 times 3. Simplify this. Again, multiply this into both. 4 plus 3n minus 3, or term n is equal to 3n plus 1. I'm going to have to shrink all of this down so that I can fit more. Ooh, that's not going to work well. Fit more onto the screen. Okay. Not the prettiest, but we can work with that. All right. Then we have to get term 1, 2, and 3 out of this. Well, term 1 will be 3 times 1 plus 1, which is 4. Term 2 is 3 times n, which is 2, plus 1, which is 7. And term 3 is 3 times 3 plus 1, which is 10. So term 1 is 4, term 2 is 7, and term 3 is 10. So we have the first 3 terms here, and we have term n, which is the general term, right here. Now we're going to write the first 4 terms of the sequence given below, and this is our first example that involves a recursive formula. So we're given the first information. Without this, we can't do it. If we didn't have this information and all we had was term n is equal to term n minus 1 plus 5, we'd know that we had to add 5 to the previous term, but without knowing what that previous term is, we'd be stuck. So this is how a recursive sequence looks. You're given the first one, term 1 equals a, we saw before, which is 4. This is how we generate the next term in the sequence, and we have to specify that n is greater than 1 because there's our first value of n. So write the first 4 terms. Well, there's the first one right there. So the second term would be term n minus 1, which would be 2 minus 1 plus 5. And again, make sure you're writing these as subscripts. Oops. Don't write something like this, because that is completely wrong gibberish. So term 2 minus 1 would be term 1 plus 5. Term 1 we know is 4. We add 5 to that, and we get 9. So term 2 is equal to 9. Term 3 would be term 3 minus 1 plus 5. So term 2 plus 5. Term 2 we now have is 9. Add 5 to that, and we get 14. Term 4 is equal to term n minus 1, so 4 minus 1. And then we add 5, so that would be term 3 plus 5. Term 3 was 14. We add 5 to that, and we get 19. So term 1 is 4, term 2 is 9, term 3 is 14, and term 4 is 19. There are all of our terms. The first, sorry, not all, but the first 4 in that sequence. All right, so that is the end of the arithmetic sequence examples for now. We're going to move on to geometric sequences. Unlike arithmetic ones, they don't have a common difference, but they have a ratio that is constant, so a common ratio. So you either multiply or divide to get to the next term. So we haven't done the exponential part of this course yet. We're going to get to that after the Christmas holidays, but this stuff will start to look a little more familiar once we get to that, because these are exponential equations most of the time, not always. Okay, so the general form is we have a, just like before, that's our first term, and then we have our common ratio, so whatever we're multiplying or dividing to get to the next term, so a times r. Then we have a times r, which is r squared, a times r times r times r, which is r cubed, all the way up to a times r to the exponent n minus 1. And the reason being that if we look at these, this is term 1, 2, 3, and 4. You notice that r is actually to the exponent 0, r to the 1, r squared, and r cubed. So it's r to the term number minus 1. So r to the n minus 1. A is again the first term, and r is the common ratio. So unlike before where we could take term 2 and subtract term 1, or we could take term n and subtract the previous term, n minus 1, now we're dividing them instead. So r is term 2 divided by term 1, or term 3 divided by term 2, term 4 divided by term 3, and so on, or term n divided by term n minus 1, whatever that number happens to be. And we'll make a note here that if r is greater than 1, meaning you're multiplying by a number greater than 1, this is exponential growth. Exponential growth. If r is between 0 and 1, so it's a decimal or a fraction between 0 and 1, it's exponential decay. And if r is less than 0, it is a geometric sequence, but it is not exponential. And when we get to that part of the course, I will show you why. We'll look at some graphs. For now, just keep these things in mind and we'll come back to it later. So, geometric or exponential sequences have a common ratio. Here is our general equation. Term n is equal to a times r to the exponent n minus 1. So that's exactly what we saw here. A times r to the n minus 1. Recursive formula, we have to start with the first thing we know. Term 1 is a, and then term n is r times the previous term, so term n minus 1, where n is greater than 1. And if we write this as a discrete exponential function, f of n is equal to a times r to the n minus 1. So it looks pretty much like this one, but instead of term n equals this, it's f at n equals this. Same thing as before, a is the first term, r is the common ratio, that part's new, and n is an element of the natural numbers, 1, 2, 3, 4, 5, and so on. So we're going to look at some examples here. All we're going to look for in this case is the value of r. So from 3 to 12, we would have to multiply by 4. From 12 to 48, multiply by 4. 48 to 192, we'd multiply by 4. So r, we could take any of these, so let's say 48, and divide it by the previous one, so divided by 12, and we get that r is equal to 4. Here we have the same numbers, but the difference is that we're multiplying by negative 4. Negative 4. So 3 times negative 4 is negative 12. Negative 12 times negative 4 is positive 48. Positive 48 times negative 4 is negative 192. So r is negative 4. From 405 to get to 135, we would have to divide by 3. Divide by 3. And divide by 3. So r in this case is not 3, but if we take one of the terms, divide it by the previous term, we get 1/3. So if you're multiplying by the common ratio, it's a whole, or I shouldn't say whole. It's a number greater than 1 like this, or it's something like this. So this one is not an exponential equation, an exponential function. This one, in fact, is, and it would exhibit exponential growth. This one would be exponential decay, where we have r between 0 and 1. Here, same idea. We divide by 4 to get to the next term. So r is equal to 1/4. And you can get that algebraically by picking one of these numbers and dividing it by the previous term. So 50 over 200 is equal to 1/4. Okay. Looking for the general term of each of these. So from 3 to get to -6, we have to multiply by -2. To get from 6 to 12, we have to multiply by -2, which means that r is equal to -2. A is our first term, term 1, so that's 3. And we know the equation looks like this. Term 1 equals a times r to the n minus 1. So term n is equal to a, which is 3, times r, which is -2, to the exponent n minus 1. Now do not, under any circumstances, think that you can multiply these numbers together and get -6 to the exponent n minus 1. Very, very, very bad math. Don't ever do that. This one is as simplified as we can get it. So this is our general term. -2 has that exponent n minus 1. 3 only has the exponent 1 here. We cannot multiply those bases together. Now the next one, to get from 7 to 1, and 1 to 1/7, and 1/7 to 1/49, we are dividing by 7 each time. Dividing by 7. Which means that our r value, whoops, did not mean to do that. R is equal to 1/7, because we're multiplying by 1/7 in order to divide by 7 each time. A is term 1, which is 7, and we're going to find our general term. So our equation looks like this, n minus 1. So in this case, term n is equal to a, which is 7, times r, which is 1/7, to the exponent n minus 1. Now, we could simplify this using exponent laws, but I haven't explicitly taught this to you guys yet, so we're going to leave it as this for now. But just note, this is not fully simplified. In order to fully simplify it, we would actually get that term n is equal to 7 to the -n plus 2. So if you want to try and figure out why that is, you can go ahead and give that a try. Otherwise, just wait till we get to the exponential part of this course. Here's another example. We're going to find term 21 of the previous sequence. So the equation that we just came up with was term n is equal to 7 times 1/7 to the exponent n minus 1. Term 21 would be 7 times 1/7 times 21 minus 1, which would be 20. So 7 times 1/7 to the exponent 20. Put that into your calculator and you're going to end up with approximately 8.77 times 10 to the -17. Very, very, very small number, because you're taking 7 and dividing it by 7 multiple times over and over and over till you get a very small fraction. Next example, determine the number of terms in this sequence. So in order to do this, we have to assume, of course, that it's a finite sequence. This is our last term, term n. So we know that it's finite. The pen is doing that thing again. All right, term n